Thank you. So this is joint work with a list of authors that's here, all of which were in Brno at some point. So yes, this talk is about something called uniform Turán density of hypergraphs. And I guess it makes sense, because this is about uniform Turán density, it makes sense to start talking about the classical concept of Turán density. So given some hypergraph F, the Turán density is the largest value of D, such that if we have a large hypergraph which has density more than D, it's the largest density of a hypergraph of hypergraphs that do not contain F as a subgraph. And the density of a hypergraph is the proportion of the R tuples of vertices which do become edges of the hypergraph. So this is a very well studied concept, very old. For graphs, this parameter has been well known for almost 80 years. A consequence of the Erdős theorem is that the Turán density of any graph depends only on the chromatic number. And to get an asymptotically optimal construction, what you take is the complete multipartite graph, which has chromatic number 1 less than the chromatic number of G. So for graphs, there's no more mystery. We already know everything that there is to know. But for hypergraphs, no such characterization is known, and in fact, it's a very bad situation. Even for very, very simple hypergraphs, such as for 3 uniform hypergraphs, the complete graph on 4 vertices, we don't know the value of the Turán density. Even take that and remove an edge, so we only have 3 edges on 4 vertices, we don't know the Turán density of that. So it turns out to be a surprisingly difficult problem. And the other parameter that I need to talk about, this uniform Turán density, turns out to behave more nicely, at least for these simple cases, in 3 uniform hypergraphs. So we add an extra condition. This variation was introduced by Erdős and Sós, and now we put this extra condition that the hypergraph that does not contain H as a subgraph has to be quasi-random. And which definition of quasi-randomness are we going to take? We are going to require that when you take a linear-sized subset of the vertex set, you see the same density as in the whole thing. And that excludes that construction of taking complete multipartite as an extremal construction, because there you have linear-sized subsets which just simply do not have any edge. They have density 0. So we want to avoid essentially just taking very sparse parts or even empty parts and just putting stuff in between them. We want really that we don't just have density in between some vertices, we really do want to have density everywhere in the graph. And then the uniform Turán density is the largest value of D, such that there exist arbitrarily large, arbitrarily quasi-random hypergraphs with density close to D, which do not contain F as a subgraph. So this is the parameter that we are going to talk about. Is it clear what the parameter is? So just like its classical counterpart, this parameter is also known for all graphs. Now the answer is always 0. It's an easy consequence of the regularity lemma, that if you have positive density, like greater than some constant epsilon, everywhere in your graph, in all linear subsets of your vertex set, then you do contain arbitrarily large cliques. But for 3 uniform hypergraphs, you don't always get 0. You can, in fact, have dense quasi-random graphs that avoid certain subgraphs. Now, the construction that motivated this definition, the one that was given by Erdős and Sós, is a bit different. It has to do with taking tournaments and just looking at the hypergraph of oriented triangles. But I am going to present a different construction because it plays a special role in the study of the uniform Turán density. It's a construction that I'm going to call the basic palette. How do you generate the basic palette? So the vertex set is going to be the numbers from 1 to n. And when I say that I take the numbers from 1 to n, the special thing about them is that they come with a certain order. So the vertex set has an order. And I'm going to take the complete graph of them, the complete two uniform graph on them, and I'm going to color those edges randomly in colors red, green, and blue. So to generate the hypergraph, for every triple of vertices, we are going to look at whether at what the colors between them are. So let's say that the three vertices are I less than j less than k. So we want the pair ij to be red, the pair ik to be green, and the pair jk to be blue, in this order. You don't need to remember the colors. We will not use them like later. But what's important is that not only do we need to see all three colors, we need to see them in the right order. So you can see that here, for the vertices 1, 4, and 6, we do have indeed the two smallest are red, the smallest and largest are green, the two largest are blue. But so we do place an edge on those vertices, but for the vertices 2, 3, and 5, we do see all three colors, but now the two smallest are blue, not red. So we don't place an edge there. We do need that the order is right. So what properties does the basic palette have? Well, you can check that for every triple of vertices, the probability that we place an edge there is the probability that we put the right colors there, which is 1/27. It's 1/3 for each of the three pairs. And using standard probability tools, you see that with high probability, this hypergraph is quasi-random. And you can also check that it does not contain a complete graph on 4 vertices, because let's say that you want to see a clique on vertices 1, 2, 3, and 4. Then the pair 2, 3, because it's containing the edge 1, 2, 3, it should be blue, but because it's contained in the edge 2, 3, 4, it should be red. That means that for the complete graph on 4 vertices, the uniform Turán density is at least 1/27. It's in fact much larger, but that's like a simple example of why it's not always 0. And why is this basic palette important for uniform Turán density? Why did I not explain that the construction that motivated the definition instead? It's because of a theorem by Ryer, Erdős and Sós. So they precisely tell you when the uniform Turán density is 0. It's precisely when your hypergraph is a subgraph of the basic palette. And as a consequence of this, there's a jump in the possible values of the uniform Turán density. Either it's 0, either the value is 0, and that means that you are contained as a subgraph, or you are not contained as a subgraph, and because this is quasi-random and has density at least 1/27, then your uniform Turán density is at least 1/27. So there is a jump. And Ryer, Erdős and Sós asked whether in this statement the 1/27 is the largest possible value that you can put in that statement and it will still be true. Spoiler for the next slide, it is. It is the maximum value. So what values does the uniform Turán density take? Certainly it cannot take all of them, all values between 0 and 1. Well, for 3 uniform hypergraphs, there's 4 values that are known. We have 1/4, which was first proved by the first set of authors using a computer-assisted proof, and then by the second set of authors just without computer. There's the 1/27, which as I mentioned, is the minimum positive value. there's 4/27, which is achieved by tight cycles. And in an upcoming paper, we will show a construction of a hypergraph with 8/27. And an important fact about this construction is that it's randomized. So there is randomness involved in the construction of the hypergraph. I'm mentioning this because the one that we are going to show today is also going to involve randomness. But that's all that's known. And if you go from 3 uniform hypergraphs to higher uniformity, nothing is known. No exact non-zero values are known. So what values make sense? So let's say that we set off to find the first value for higher uniformity. Where do you look? Well, we can try to generalize this basic palette to higher uniformity. And, well, there's not just one way in which you could generalize it. So do we color, again, the pairs of vertices? Or do we now color the r-1 tuples of vertices? Or do we actually color every level? So we color both pairs of vertices and triples of vertices and quadruples of vertices all the way to r-1 tuples of vertices. There's many ways in which, there's many possible generalizations of the basic palette that a priori make sense. But if you think for a few minutes about the implications, about what, like, could this be a possible characterization of hypergraphs with uniform Turán density 0, you see that if any of those make sense, then it should be the one where you're coloring the pairs of vertices. And you should be, so just like before you used 3 colors, now you should be using R choose 2 colors. And you want to essentially force that each pair of vertices in, that each pair of vertices in any edge gets one of each color, and that they always come in the same order. So there's, let's say that here the color red is always going to come between the first and second vertex. The color green is always going to come between the first and third vertex, and so on. And if you use that construction, well, then you can see that the resulting hypergraph has density r choose 2 to the power of minus r choose 2. And with high probability, it is quasi-random. So it makes sense that, well, if, it's a reasonable conjecture that if for 3 uniform hypergraphs, the minimum value of the uniform Turán density was 1/27, that in this case, it will be r choose 2 to the power of minus r choose 2. It's a reasonable conjecture. In fact, I made this conjecture when I was presenting the 1/27 result. And you can split it into 2 parts. Like, we have an upper bound and we have a lower bound. For the lower bound, you would need to prove the characterization that hypergraphs which are subgraphs of the basic palette are precisely those which have uniform Turán density 0, and therefore you have this jump. That would be the lower bound. And for the upper bound, you would need to prove that, well, you would need to construct a hypergraph which has exactly this value as the uniform Turán density. Now, when I was giving that talk about the density 1/27, I ended with these 2 conjectures as open problems, and I was mentioning that the first conjecture seems, okay, it's hard, but it's doable. Like, if someone uploads to archive someone saying that they have solved this problem, I would not be that surprised. Like, I think it should be doable. But for this one, I essentially didn't see a path of solving it without having already the solution of the first one. But it turned out to be wrong. In fact, it is very much possible to prove this one without proving the first one. So indeed, there was something that I was missing. There was something that I didn't realize. So yes, this is essentially the main theorem of this talk, you could call it, but of the paper that will will contain the results of this talk. However, the result that I'm going to sketch the proof of is not going to be this one. It's a bit easier. It just says that for all uniformities you have hypergraphs with uniform Turán density 1/4. It's basically a simpler proof, and in the end, if I have time, I can sketch the differences between the two proofs. So why 1/4? Again, where does this value come from? It should come from a certain extremal construction. So in this case, we are going to color the pairs of edges not with R-choose-2 colors, but just with two colors, red and blue. And for an R tuple of vertices, we are going to call the pair of the two leftmost vertices, it's going to be the head, and the two largest vertices are going to be the tail. So these are the head and the tail of an edge. And we are going to place an edge there if the head is red and the tail is blue. And you can see that the probability that we place an edge is indeed 1/4. And for the same reason, the hypergraph that you generate is going to be quasi-random. So you want to look for hypergraphs that do not appear here, but appear in anything that is strictly denser than this. And fortunately, there is an easy characterization for which hypergraphs do not appear here as subgraphs. So in this hypergraph, the easy thing to notice is that you will never find a pair of edges such that the head of one is the tail of another, because then the intersection pair should both be red and blue. So we can say that a hypergraph is head-tail mixing if no matter how you reshuffle the order of the vertices, you always see a pair of edges that intersect precisely in this form, precisely heads with tails. So we can start making, so certainly any head-tail mixing hypergraph will not be contained in the construction above, and therefore the uniform Turán density will be at least 1/4. So we can start making a list of things that we want our hypergraph to satisfy, and then at the end we can start to worry about whether such a hypergraph exists or not. So this property of being head-tail mixing guarantees that the uniform Turán density is at least 1/4, and next we want to impose conditions that force it to be at most 1/4. And now it's time to delve into what I didn't want to go into. I've been mentioning for a while about some problems are easier, some problems are harder, some problems I expected to be easier, or I expect them to be hard. How can you know how can you take a guess of whether a problem is easy or hard without solving it? So let me show you. I told you that Turán problems are much harder on hypergraphs than on graphs. That's just basically something that the last 80 years have proved. I told you that sometimes uniform Turán density problems on free uniform hypergraphs are easier than Turán problems, than classical density problems. But I told you that intuition, like that advantage, is lost when you go to uniformity higher than 4, higher than 3. I also told you that I expected that characterizing hypergraphs with uniform Turán density 0 would be easier than showing the existence of a hypergraph with density R-choose 2 to the power of minus R-choose 2, but then that intuition turned out to be wrong. So what makes some problems easy and some problems hard? It's the hypergraph regularity lemma. So how many of you are familiar with how the hypergraph regularity lemma works? Not really would be able to state it, just they are familiar with the structure of the things, of the partition that it gives. And I see that, yeah. Yeah. So the regularity lemma for graphs, so you input some very large graph and it returns a partition of the vertex set. A partition in which all the parts are essentially equal. And it has the property that for every pair of parts, so let's say that between V1 and V3, or actually not for every pair, but for almost all pairs of parts, the bipartite graph that you get between them is quasi-random in a very similar condition as the one that I introduced earlier. So that's for graphs. If you're working with 3 uniform hypergraphs, not only do you get a partition of the vertex set, you also get a partition of the set of pairs of vertices. And in a certain way, this is a partition that refines the first one, in the sense that if you look at the pairs of vertices between V1 and V2, for example, you get a refinement of that. Between V1 and V3, you get a refinement of that, etc. If you are working on 4 uniform hypergraphs, you always also get a partition of the set of triples of vertices, which refines the second layer in the sense that, triples of vertices here have 1 pair in this part alpha, 1 pair in this part beta, 1 pair in this part delta, for example. So each layer essentially is a refinement of the previous one. And if you're working with R uniform hypergraphs, you go all the way to partitioning R-1 tuples of vertices. And the key to what makes some problems easy and some problems hard is that problems tend to be easier if you only need to work on 1 layer of the regularity partition. So first of all, that explains why problems on graphs tend to be easier than on hypergraphs, because you only have 1 layer. And the magic of uniform Turán density, the magic of adding this quasi-randomness condition, is that you essentially remove the bottom layer because all the vertex sets essentially look the same. You get the same density for all of them, so you don't really need to care about which part of the bottom partition you are working on. It's slightly more complicated than that, but it really just removes that layer. So that explains why in 3 uniform hypergraphs, uniform Turán density problems tend to be easier, because now we are only working on 1 layer. And we also lose that advantage when we go to 4 uniformity and above. So then, how do we tackle this problem? Well, one possible thing that we can do is to say, okay, let's strengthen the quasi-randomness condition, let's make it something stronger, so that it's not just all sets of vertices that look the same, but all sets of R-2 tuples of vertices look essentially the same. That way we would remove all layers except the very top one. Indeed, this is something that you can do. I'm not sure whether Erdős and Sós considered it, but certainly Reyer, Rödel, and Schacht already looked into this extra condition. And in fact, Lin, Wang, and Zhou gave the minimum positive value of the uniform Turán density in this strengthened quasi-randomness condition. But let's say we don't want to change the quasi-randomness condition. We want to just keep that linear-sized subsets of vertices have the same density. What do we do then? Well, there is a way of only working on 1 layer. Let's suppose that we are free to choose what graph F we pick. That's the whole point of making this wish list. So let's say that we require that any pair of edges intersecting at most 2 vertices. Then essentially we don't need to care about layers 3 and above, because any triple of vertices will be containing at most 1 edge. Any quadruple of vertices is going to be containing at most 1 edge, and so on. So we only need to care about the bottom 2 layers, but because we have the quasi-randomness condition, we are also removing the bottom layer. So we are, in fact, only working on one layer. And the intuition should tell us that that should make the problem easy. So that's one extra condition that we can add into our list. We can require that any pair of edges intersects in at most 2 vertices. And that is something that we cannot do for the characterization conjecture. So that explains why out of the 2 conjectures, it's actually the top one that is harder. Okay, but just adding this is not going to solve the problem. It's not going to magically give us a hypergraph with uniform Turán density 1/4. We still have a bit of work to do, but we are getting there. Now we need to look at quasi-random hypergraphs which have density strictly greater than 1/4 and ask ourselves, what do we find there? What happens when we have density strictly greater than 1/4? And the answer is that you always get a pair of edges that intersects head with tails. You can get this by double counting. So essentially you take some vertices in the middle, you ask how many of those pairs of vertices must be the head of an edge, how many of them should be the tail of an edge, and by pigeonhole principle you get that there must exist a pair that is both a head and a tail, and that gives you this configuration. So we always find a pair of edges that intersects heads with tails. So now you go to the regularity partition and look at each family of 2r-2 vertex parts. And you ask, do I see this picture there, or do I not see this picture there? And we can apply Ramsey's theorem to this statement. Do I see this figure? Do I not see this figure? It's not possible to have a very large family of parts in which we never see there, because we can apply that double counting argument. So Ramsey's theorem should return a large family of vertex parts in which we always see this. And actually, that's very, very good, because it means that if our hypergraph is made of almost disjoint copies of this thing, meaning we take copies of this thing that are allowed to intersect in at most one vertex, then we can find that in the hypergraph. Because essentially, we only need to fix in which part each vertex lies, which we can do arbitrarily. We only need to fix where the pairs of vertices that are contained in a pair of edges lie, which we can do because we know that there exists a pair of edges that looks like this in any 2r-2 tuples of vertices. And that's all that we need to care about for now we can apply the counting lemma, and it will tell us that, okay, so a hypergraph like this will exist. A copy of your hypergraph will exist. So that completes the list of the requirements for our hypergraph. First of all, it has to be head-tail mixing. Whenever you shuffle the vertices, you get a pair of edges that intersects heads with tails. Second of all, we want that every pair of edges intersects in at most 2 vertices. Third condition, for every edge there exists exactly one other edge that it intersects in 2 vertices. That means that it's made of almost disjoint copies of this graph. And final condition, there exists an ordering of the vertex set in which all intersection pairs look like this, heads with tails. Those are our conditions. And now we can ask, does such a hypergraph exist? Well, satisfying the last 3 conditions at the same time is very easy. There's a very easy way of constructing hypergraphs that satisfy them. You start with, because if you essentially merge each copy of this into a single edge, now every edge will have size 2r-2, and it will be a linear hypergraph, meaning that any pair of edges intersecting at most one vertex. So we can reverse this process. We can start with a linear 2R minus 2 uniform hypergraph, take a fixed ordering of the vertex set, and just split each edge into the first R vertices and the last R vertices. Then it will be true that any pair of edges intersects in at most two vertices. It will be true that for every edge there exists exactly one other edge that it intersects in two vertices. And it will be true that there exists an ordering in which all intersections of size 2 are heads with tails. And the only thing that we need to worry about is whether this hypergraph is head-tails mixing. Meaning that we need to check that for every permutation of the vertex set, there exists one of those pairs that intersect in size 2 that still intersects heads with tails. Okay, what can we do about this? Well, it would be enough if for any permutation of the vertex set, there exists an edge on which this permutation is monotone. Because that way, the picture, either the order is increasing, in which case the picture on the right remains the same, or the order is decreasing, and then the picture on the right is exactly reversed, but because it's symmetric, it remains the same. So what do we know about monotone subsequences in a permutation? Of course, the first thing that comes to mind is the Erdős theorem. There always exists a monotone subset of size square root of n. So if we can find a linear hypergraph such that in every subset of size square root of n vertices we contain an edge, we are done. Unfortunately, Kleffmann and Rödel proved that you always have an independent set of size of order square root of n log n. So that's unfortunate. But there's some extra things that we can do. So I am going to tell you which family of linear hypergraphs satisfies this property, and then I will prove that indeed it satisfies. The condition that we want is that we want this family to be nowhere empty. So what do we mean by that? Let's say that we are looking for an R uniform hypergraph, and we take R subsets of vertices, R disjoint subsets of vertices, which are disjoint, and each of which has size linear in n. Then if the sequence of hypergraphs is nowhere empty, there will be some edge that contains one vertex in each of them. And I just want to point out that there exists indeed a nowhere empty sequence of linear hypergraphs, which you can obtain by taking G and P, or the Erdős-Renyi random hypergraph for a very specific value of P, and just remove every edge that intersects another edge in two or more vertices. It's a very standard method of alterations proof. So such a sequence of linear hypergraphs exists, one where you can take any family of linear-sized subsets of vertices, and you are guaranteed to always find an edge that hits each of them in one vertex. So all that's left to do is proving that any nowhere empty sequence of hypergraphs has the property that when you reshuffle the vertex set, there is one edge that remains monotone. To prove that, we will use a problem from 2017. And this phrase should sound weird. What do you mean we use a problem from 2017? Do you mean we use a theorem? No, I mean very literally, we use a problem. Specifically, problem 5
What?
from the International Mathematical Olympiad. Yes, we are going to use an IMO problem. And this is the statement of this IMO problem. So, I don't know if you can read. We have n times n plus 1 soccer players, which are standing in a row, and no two of them have the same height. And Sir Alex, I don't know who this is, wants to remove some of those players and leave only 2n of them, with the property that the two tallest players are standing next to each other in the new row. The third and fourth tallest players, the third and fourth tallest players are also standing next to each other in the row. The fifth and sixth tallest players are also standing next to each other, all the way down to the two shortest players, which are also standing next to each other in the row. It's a very beautiful problem. Usually I would give you 1.5 hours to think about this problem, but I don't think the talk goes on for that long, so I will just give you the solution. So remember that we start with n times n plus 1 players. So one thing that we can do is we are going to split it into n blocks, each of which has n plus 1 players. And we can just require that, or just say that in the end, we will have 2 players from each of those blocks. It's a condition that we can add. And then what we do is we start taking players from tallest to shortest until the first time that we hit a second player from a block. Then we fix those 2 players and drop all the other players that we have selected so far and all the other players from the same block. What has happened, and we call this the first round. What has happened in this first round, from each block, either we already selected 2 players and we are done, or we dropped at most 1 player from that block. So we just repeat the procedure. We keep going until we hit 2 players from the same block. Then we fix those 2 players and drop the other selected players. Because there are n plus 1 players initially in each block, and we drop at most 1 of them in each round, after n rounds we cannot have run out of players, so it will mean that on every block we will select 2 players. And that's the proof of the statement. So now, what does this have to do with the problem of that we were talking about with uniform transdensity? So remember what our goal is. We have some hypergraph which has this property that of being nowhere empty, and we want to show that in every permutation of the vertex set we can always find an edge in which this permutation acts monotone. So we can essentially plot these vertices. Here on the x-axis I have the original order, and on the vertical axis I have the new order, the permutation. And we are going to start by splitting the vertex set into several blocks. Now I'm going to split it into r square blocks, each of which has size n over r squared. And once again, we are going to go from top to bottom. We are going to start picking vertices, and now rather than stopping the first time that we see 2 vertices in the same block, we are going to stop the first time that we see n divided by r to the 4 vertices in the same block. So and then we drop all of the other selected vertices. So what has happened in this first round, from each block, either we already selected n divided by r to the power of 4 vertices, or we dropped fewer than n divided by r to the 4 vertices. And then we repeat again. The first time that we see n divided by r to the 4 vertices from the same block, we fix those and drop the rest. And by the same argument as before, we know that at the end of the procedure, from each vertex class, from each block, we have selected n divided by r to the 4 vertices. And it has the properties that if you take the convex hull of each of them, their projections of on the x-axis are disjoint, and the projections on the y-axis are also disjoint. So now we can contract each of them into a single vertex, and because we have r square vertices now, r square blocks, we can apply Erdős segregation. And we find now a monotone sequence of blocks. But each of these blocks has size that is linear in n. So by the nowhere empty property, it means that there exists an edge that hits each of them in precisely one vertex, and therefore this edge will be monotone in the permutation. And that concludes the proof of the theorem that there exists a hypergraph with uniform Turán density 1/4. So now I could mention what changes you have to do in order to prove this statement about r choose 2 to the power of minus r choose 2. So I expected this to be like close to the end of the talk, which is why I have the thank you slide here. So I'm going to stop here for a moment, or at least. So I am going to I would rather go to questions now, and if anyone wants to ask about what changes you need to do for the case of r choose 2 to the power of minus r choose 2, I can keep going. But for now, that's all. So thank you.
Okay, the first question is, how do you do that?
Okay. Yeah. Yes. So this was all done on the assumption that the extremal construction was this one in which you never get intersection where the head of one edge is the tail of another edge. So now we have to run the same argument based on the idea that the extremal construction now is the one where we use r choose 2 colors, and we use one for each position, for each pair of positions within the edge. So, of course, the first condition is going to be whenever, the equivalent of being head-tail mixing now will be whenever we take any permutation of the vertex set, we can always find two edges which have intersection size at least 2, or once we add the condition that the intersections are at most 2. So we want a pair of edges which have, in fact, intersection size 2, where the intersection pair is not in the same relative position within each of those two edges. Meaning that, for example, we want them to intersect. If you think of these as a red edge and a blue edge, where the purple two vertices are the intersection, you can see that among the red edge, this intersection pair is the 3rd and the 6th vertices. Whereas within the blue edge, we have the 2nd and the 5th vertices. So we want to always be able to find a pair that intersects in something like this. Or like in the second row, where we intersect 4th and 6th with 3rd and 6th, but not something as in the last row, where we intersect 2nd and 6th with 2nd and 6th. So anything like in the first two rows would be fine, but something like in the 3rd row is not what we want. So then the upper bound comes from fixing that, or actually the lower bound comes from fixing that in any permutation we see something that looks like one of these rows. And then you have the other condition. What do you always see once you go above this threshold? And well, the thing that happens is that you always see some edge that intersects in some of these ways. And using the Ramsey statement, you can make sure that not only do you see such pair on every 2r minus 2 tuples of parts of the regularity partition, But in fact, you can also force that all of them are of the same type. So maybe all of them are of this type, or maybe all of them are of the second type. You can fix that all of them are of the same type. Why not? It's Ramsey's theorem. We can just make everything equal. So for the lower bound, you want to make sure that there exists an ordering of the vertex set in which all of those pairs of edges that intersect, which have intersection size 2, in some order, all of them look like the first row. And in some order, all of them look like the second row. And for each way in which they could intersect, which is not somehow like the bottom row, for each of those ways, there exists an ordering in which all of those pairs simultaneously look like that. So the hard part is essentially how to take care of all of these orderings. And the idea here is to take the vertex set to essentially be like a hypercube. And then you want that when you sort the vertices from left to right, all those pairs of edges look like the sequence on the bottom. When you sort them from bottom to top, you want to always see this sequence. And essentially, you will also start, the way that you get the construction is you will also start by taking nowhere empty linear hypergraph. And now, rather than splitting every edge into two, you only split the pairs of edges. You only split the edges in which you can color in such a way that all the projections onto each axis looks like the corresponding sequence. And then it becomes much more complicated because now, rather than using the Erdős theorem, you need to use multidimensional Erdős theorem, which was proved by Fishburne and Graham, which essentially tells you that if you have any ordering of the hypercube, you can find a smaller hypercube which is sorted by layers. So those are like the basic ideas of how to generalize. Like basically, stuff just gets more complicated.
Oh, so
those are the changes that you would like. Those are the changes that you would need to do.
I see. Thank you. Second question? Any other question?
So far there's no Turán densities known when we have two rows that we have to take care of in this.
No, I don't think any result in that direction is known.
So when you choose the basic palette for higher uniformity hypergraphs, you just coloring the every pair of edges, but when you consider about the four uniform hypergraphs, for me it seems more natural to consider coloring the triple of the colors.
Yes.
Why you?
The reason for that is that if you do not change the quasi-randomness condition, the reason is that if you know what position each pair of vertices should be in, then that immediately forces where each triples of vertices should be in an edge. Essentially, knowing the position of every pair of edges just forces everything else, forces the upper. Like ideally, you would in fact force the position of every vertex, but that's not something that you can do precisely because of the quasi-randomness condition. That's essentially the reason why for Turán density, for the classical Turán density, the answer for when do you have classical Turán density 0, it's when you are R-partite. So you have a partition of the vertex set such that each edge hits each class exactly once. And that's essentially the same as coloring the vertices rather than the pairs of vertices. Once you go higher in the uniformity, now you need to color the pairs of vertices. If you go very high in the uniformity, so you might have noticed that in this result, here, the value that we get is r to the power of minus r. That's of course because you are coloring with r colors and you want a very specific pattern of colors to get. Any other?
When you have let's say you have set up all uniform Turán densities of R graphs,
Mm-hmm.
can you tell whether there's any accumulation point?
So actually I believe that it should be true that there exist accumulation points. Certainly, so I think there's a conjecture that for the classical Turán density, the minimum positive one is an accumulation point. At least it's known that if it is a jump, it should be a very, very tiny jump, even for 3. And I think there's a way of, like, at least I have an intuition for how to relate jumps in classical Turán density with jumps with uniform Turán density.
Like, will there be
So I would
many,
expect.
or will there be infinitely many such points, or we have no idea, right?
Yeah, I don't really know. I have vague ideas about like some arguments for why it makes sense for things to behave like this, but basically only in very specific cases.
Other questions? So for that, let's thank the speaker.